In this problem, we have a solid sphere of radius a, which is 2 centimeters. This sphere is concentric with a spherical conducting shell of inner radius b and outer radius c. So first we need to find the charge density of this solid sphere. What is the charge density? How do we find the charge density? This is the volume charge density, charge for unit volume. The total charge is q, and if we divide that by the volume of that sphere, volume is 4 divided by 3, 5, radius is a cube, that gives the charge density. So let's write down the Gauss law. Gauss law says epsilon naught times the net flux coming out or going in through a Gaussian surface, closed Gaussian surface, equals to charge enclosed by this Gaussian surface. So this is the epsilon naught times the net flux, that is net flux, net electric flux equal to charge enclosed by that Gaussian surface. So if you consider very tiny Gaussian sphere, the center of that Gaussian sphere is at the center of this solid sphere, and radius is almost zero, negligible, then what is the charge enclosed by that Gaussian surface when radius goes to 0? Charge is 0, no charge enclosed by that Gaussian surface. Then no electric flux coming out from that Gaussian surface gives that the electric field is 0. When R equals 0, no charge enclosed by the Gaussian surface, so electric field equals to 0. Now let's consider the second situation, B. We need to find the electric field when R equals a by 2. So this is A, and a by 2 is somewhere here. So I'm going to find the electric field there. You can consider a spherical Gaussian surface. Radius of this Gaussian surface is a by 2. The center of the Gaussian surface is at the center of this Gaussian surface and the center of this sphere, they coincide. Then we can apply Gauss law to get the electric field at that location or on the surface of that Gaussian sphere. So from the symmetry we can see, so this is the Gaussian surface, and electric field lines are going radially outward because this sphere is positively charged. Gaussian sphere. So I'm going to consider small area element on the Gaussian sphere, and these are the electric field lines going radially outward. And you can see, if you consider a area element on this Gaussian surface, the electric field vector and the area vector, they are parallel to each other. So E times E dot dA equals E times dA times cosine theta anywhere on the surface of the Gaussian sphere, because area vector and the electric field vector, they are parallel to each other always. Then I can write the Gauss law to this Gaussian surface. The radius of this Gaussian surface R equals a by 2. Then epsilon naught times E dot dA equals E times dA times cosine 0, which is 1, E times dA equals charge enclosed by this Gaussian surface. How do we find that? If we know the volume of this sphere, then we can find the charge enclosed by that Gaussian sphere. The charge density is rho. The volume of that sphere is 4 divided by 3 phi. A divided by 2, A divided by 2 is the radius cubed. That is the total charge enclosed by that Gaussian surface. Now I'm going to continue my work here. Epsilon naught E, I can take the E out from the integral because on the Gaussian surface, the magnitude of the electric field is the same everywhere. Integration of dA, and this integration gives the total surface area of this Gaussian sphere, which is 4 phi r squared. R is A by 2, so A divided by 2 squared. That equals 4 rho phi A cubed divided by 3 times 2 to the power 3, which is 2 times 2 times 2, 4 times 2, that's 8. Then I can write epsilon naught E times 4 phi A squared divided by 4 equals 4 rho phi A cubed divided by 3 times 8, that's 24. So I have, we can cancel this commons for both these terms, phi 4, here we have A squared, here you have A cubed. Then I can write epsilon naught times E divided by 4 equals rho A divided by 24. That gives electric field equals so this is 1, this is 6 rho A divided by 6 epsilon naught. That is the electric field, and this is radially outward. This is our rho, the volume charge density, 3q divided by 4 phi A cube, 3q divided by 4 phi A cube times A divided by 6 epsilon naught. I can write electric field Q equals Q divided by 8 phi epsilon naught A squared. That is the electric field. Direction is radially outward. When R equals to A, what is the electric field? So when R equals to A, we have to consider all the charges on this spherical or the solid sphere, non-conducting solid sphere, because we need to find the charge or the electric field on the surface of this solid sphere. So we have the solid sphere, and radius of the solid sphere is a, and we want to find the electric field at this point. And from the symmetry we can see these are the electric field lines on the surface of the sphere. These electric field lines are always perpendicular to the surface. If you consider small area vector on here, we can see electric field vector and the area vector, they parallel to each other. So we can use the Gauss law, and this time the Gaussian surface is a sphere which is slightly bigger than the or which is the outer surface of the solid sphere, the surface of the solid sphere. So let's do it really quick. Epsilon naught times, we know that E dot dA is E dA is constant, so you can take that out. The dA, integration of dA, which is the surface area of this sphere, and charge enclosed by this sphere is Q, which is 5 picocoulomb. So this is Q, positive charge. So E equals Q divided by epsilon naught times the surface area of the sphere, which is 4 5 A squared. E equals Q divided by 4 5 epsilon naught A squared. The direction is radially outward. So that is the electric field when R equals A. When R equals to 1.5 A, that is somewhere here, it in between the that is a point in between the solid sphere and the conducting spherical shell. What is the charge? Okay, so what kind of Gaussian surface we going to select? Again, a sphere. Center of the sphere is at here. The radius of this sphere is 1.5 A. R is 1.5 A. And what is the charge enclosed by this sphere? That's Q. So we have the charge enclosed by the Gaussian surface. Charge enclosed is Q. That's equal to epsilon naught times E dot dA. Again, we know how to evaluate this dot product, and then we can get Q equals epsilon naught E integration of dA, which is nothing but the surface area of the Gaussian surface. And I can write the electric field E equals Q divided by 4 5 epsilon naught 9A squared 9 A squared divided by 4. That is how you find the electric field at 1.5 A. Now we're going to find the electric field at a point where R equals 2.3 A. So inner radius is 2A, outer radius is 2.4 A. So we're going to get the electric field somewhere here. So we're going to consider a Gaussian surface, which is again a spherical Gaussian surface. The center of the Gaussian surface is here, and the radius of this Gaussian surface is 2.3